Yeah, recorded is rolling. Welcome to Thursday, getting near the end of this week. So gonna wrap up some relativity ideas today. We're about to do a Kahoot, gonna finish that relativity page, finish class with maybe some bonus demo. I do want to mention science courses. Where's, all right, so you guys have probably, through your English classes, gotten course registration pages recently. All right, so I want to mention those real fast because we're working on a new system this year that's been different from past years. All right, so let me show you past year system, not because it's exactly relevant to us right now, but here, that makes sense. So in the past, the way the systems work is I ask you what science course you want, and then I have all your names here, all the available science electives, you check a box, and then I do stuff on my end. Okay, that's not what we're doing this year, but since I do have this printed out, at least I do have a nice list of science electives, so we can go into these real fast. I can tell you a little bit what I know. I'll do. So to graduate, the graduation requirement is that between science and social studies, you have to collectively have 7 credits, like 7 classes. So you could do 3 science and 4 social studies or vice versa. And by the time you guys are in this class, physics, you should have had at least 3 science classes, right? Biology, chemistry, and then this class physics. Right, so yeah, we've got all these electives that you could possibly take. Anything that's advanced placement, of course, you could possibly get college credit for. Of course, those are really hard classes too. And since the government's paying for it all, it's free. So because I know like some students like to have gaps in the schedule senior year. Maybe there's an advantage to that if you want to use a gap in your schedule, like oh, I don't have any classes during the morning or afternoon break. If you're using it for some reason, that could be a good idea. But if like, why not? Pick up some extra knowledge. It's all paid for, right? Because you go to college, you have to start paying for credits and stuff, right? So go left to right here. So here are 5 AP courses in science that are offered. Now, if you do AP, advanced placement, of course, you could possibly end up with science with college credit if you end up passing the exam. I know Physics 1 has a pass rate of 40%, both nationally and also this school each of the last 2 years. It's about 40%. So there's no sort of what you're getting to. Okay. Of course, huge workload, lots of studying, the whole thing. Also, I've seen this form circulating. I think this is a consent form to join AP. Basically says that going into an AP class, the class is really hard and it takes a lot of studying and blah, blah. And if you, okay, so there's some details about that. But if you were interested in doing an AP class, then let me know and get you hooked up with one of those forms and figure out from there. So there's AP Biology, AP Chemistry, AP Physics 1, that's a class I teach. Actually, all the stuff I've taught you guys so far is pretty similar topics to AP Physics 1, except it goes more in depth and it's a bit harder. Math is a step up. AP Physics 2 is, Mr. Gentili teaches that one. So that covers topics like electromagnetism, electric fields, circuits, there's waves, thermodynamics, fluid dynamics, optics, those sorts of things. There's AP Environmental Science. Want to take that? Okay, so those are the AP classes. How about other science electives? We got Environmental Science. There's Marine Science class. So you could do Marine 1 and then followed by Marine 2. There's Anatomy, Forensic Science. Now, science research is kind of an involved class. Who in here is in science research? Anybody in here in science research? Okay, so this is one where you put together a presentation for a science fair. So you might be working extra, say on weekends, and then you're going to put together a presentation. So like probably February next year, you go present it at the mall or something. Right? And you could possibly win scholarships with this too. So it's one of those classes like AP takes a little extra effort. But there could also be a pretty good reward at the end if you do a really good job with your project. Okay? So anyway, that's what the school offers. there you go. Do you guys have any questions about what any of these classes or any details are here? All right, so yeah, just got to glance at that. But like I said, this year we're not doing this method. It's all through you guys. You get a form, you get to check your own boxes. And if you do want to sign up for AP, I think I do have to sign off for if you want to do AP. So if you're interested and you want it to be dedicated to something like that, then let me know and yeah, can sign off for you. All right, so let's get back to, we're doing relativity. We're gonna hit this Kahoot, then we'll go back and finish this page, and yeah, we'll see where we are in class. All right, so flip the screen over, share screen 2. Oh, well, I don't know what happened to the screen here. All right, flip back and forth. So sometimes this fixes it. Yeah, we're back. Okay. So got 20 questions lined up on special relativity. So think about what you learned last few days. There's some dilation questions, like time dilation, length dilation. You guys remember the twin paradox? Which twin appeared to age quickly, turned to an old man? Was it Earth twin or was it rocket twin? Earth twin, right? Earth twin, stay on Earth, time beat by really fast for him. Rocket twin moving at a relativistic speed, time slowed down. Okay. But you guys remember too, that if you're along for the ride with rocket twin, you don't notice anything weird inside the ship. Time still beats at 1 second per second. It's just when these two twins are looking at each other through telescopes that they see each other's clocks moving at different rates. You guys remember the train paradox, the train going through the tunnel? And if you're an outside, I should say, inertial observer, an observer in inertial frame of reference, looks like the train shrinks, it goes into the tunnel. If you're on the train, then the opposite happens. It looks like the mountain shrinks and the train waits. All right, so a few reminders. Oh, there was a mass energy equivalence. There's some questions about that. E equals mc squared. That's the energy of nuclear reactions. All right, let's get this party started. In contrast to an object with mass, no matter how fast the source of light is moving, light always has the same speed, right? 3 times 10 to the 8 meters per second. That's related to that Michelson-Morley experiment I told you guys from the 1880s, right? Light has the same speed no matter what, regardless of the speed of the observer. At least to Einstein, who reasoned that that all those statements would be true. Right, so all motion is relative, and how fast is something moving? Well, you can only measure speeds or velocities relative to other objects, right? There's no such thing as a speed relative to like the center of the universe. There is no such thing. A spaceship moves away from a station at half the speed of light. If a person in a space station flashes a light beacon, people on the ship will see light traveling toward them at a speed of what? The speed of light. Remember, the speed of light is the same regardless of your frame of reference. So if you're on that ship moving at the speed of light and you break out the Toots wheel and do the whole Fizeau experiment, you get the speed of light is the speed of light. If you're based on a planet and the spaceship whizzes by and you break out your Toots wheel and measure, you still get this. Everybody agrees on what the speed of light is. And then Einstein said, well, the only thing that makes it consistent is that people experience different passages of time, right? Suppose you observe a spaceship whizzing past you at, say, a relativistic speed. Compared to what the person in the spaceship sees, we see the spaceship clock is running. So we are Earth twin, we break out a telescope, we look through the window of the spaceship and see the clock doing what? moving slow. Right? Remember how Rocket Twin barely aged at all, and Earth Twin turned into an old man, right? So we see the spaceship clock is running slow. If you're moving high-speed spaceship relative to Earth, you would it would be above. Remember, Rocket Twin inside the ship doesn't know when there's anything weird about the ship or inside the ship itself. So, in Rocket Twin's frame of reference, everything is just like in this room. According to special relativity, all laws of nature are the same and reference frames that move at constant speeds. The technical name for that is called inertial frame of reference. Inertial frame of reference. Okay? So once you start accelerating, that leads to changing velocities, which kicks off the whole dilation process. Clocks on a spaceship moving very fast appear to run slow when viewed from from Earth. So Earth Twin sees Rocket Twin's clock's running too slow. You're actually looking into the past. All right. So actually, whatever your answer is probably a good answer because now Starlight definitely would be true. So if you pick the right one, then that's actually not a terrible answer. Because Starlight, you're looking at many light years into the past. It took many years for that light to cross the galaxy to reach us. Now, the blue answer is also technically true, right? If, so look into the screen right now. Maybe you're looking at like, I have to do the calculation, but maybe like a nanosecond into the past, something like that. So yeah, you're always looking into the past, just more into the past the further the distance, I think. When you approach a light source, the wavelength of the emitted light, ooh, this sounds like the Doppler shift. Just remember red shift, blue shift. Okay. When you approach a light source, where does that go? Yeah, that wavelength would get shorter. I should have switched those answers because shorter would be blue shifting, wouldn't it? Right? And then longer would be red shifting. So just make the colors consistent with the actual phenomenon, right? I need to go back and fix that question. And some frame of reference to the universe, you are traveling close to the speed of light. True. In fact, I have a picture of a location where that happens to be true in this classroom, and it is right there above the door. You guys see the Hubble Ultra Deep Field? You see all those galaxies right there? That is the edge of the observable universe. All those galaxies relative to us are moving almost the speed of light away from us. And there are almost certainly galaxies beyond us moving faster than the speed of light. So the light from them will never reach us because of universal expansion. So if there are any beings on any of those galaxies, probably are, maybe. But if they're looking back at Earth, then they would see us moving at the speed of light relative to them. Friend riding on the back of a truck that is going away from you at 25 kilometers per hour. After the truck passes, your friend throws a ball toward you at 55 kilometers an hour. How fast is the ball going relative to you? This is just plain Newtonian relativity. Okay, so you could have answered this last semester. So 25 one way, 55 the other way. The difference is 30, isn't it? Right? Because opposite directions. Right? So 25 one way, 30. If the truck's moving forward, you throw the baseball backward when you subtract this. Right? So that's just plain Newtonian relativity. Last semester kind of stuff. To a person who is inside a spaceship moving close to the speed of light, the meter stick held horizontally and the ship looks. Okay, so you are a rocket twin, you're traveling on with the rocket. What does the rocket look like to you? No, just the same. Remember, if you're along for the ride, you don't notice anything about anything that's moving. You don't notice anything weird about anything moving along with you. You only notice these dilation effects from an inertial frame of reference, okay, outside looking in. To calculate how much rest energy an object contains, yeah, that's E equals mc squared. You guys go. Everybody getting that? Objects accelerated to relativistic speeds appear to what? Length dilation. Remember that train going through that tunnel? Oh, sorry. My clue was not very helpful. All right, I'm thinking. Sorry about that. All right. So now the train did appear to get shorter from an inertial frame of reference. That's the opposite of the red one. Right. It would also, if you think about the twin paradox, would appear to, remember, rocket twin looks like he barely ages compared to Earth twin. So it's the opposite of the yellow one. You know what? If you got the blue one, I couched this a little bit differently in the equations I told you. I told you guys about a mass dilation. You guys remember mass dilation? Okay. Well, isn't momentum just mass times velocity? Some textbooks, including Paul Hewitt textbook, and that's where I grabbed all these questions from, actually teaches it in terms of momentum, like momentum dilation. So there you go. So gain momentum, gain mass. Standing on the ground, see a rocket ship speed by at 95% speed of light compared to the rocket at rest. What do you see the rocket length? Short rocket. That would have been a good, the train going through the tunnel would have been a good clue for that one. Remember length dilation, something speeds up, it appears to get shorter. If you multiply by the Lorentz factor, which is between 0 and 1, instead of dividing. When an object is pushed to relativistic speeds, it's momentum dilation, right? Mass dilation. What happens to mass or momentum? Yeah, it appeared to increase. You guys remember I showed you those graphs yesterday, right? Those vertical asymptotes. Right? You know, that was for both time and for mass. And okay, mass goes hand in hand with momentum. Okay? Yeah, if you approach the speed of light, mass or momentum would tend towards infinity. Remember I told you guys particle physicists over at CERN see that all the time. They run particles near the speed of light and appear to gain mass. You may have heard, I don't know, did you guys see a few years back, there was a concern that scientists over at CERN might accidentally create a black hole I don't know if you saw that story, but that might be why, right? Because if you're running particles near the speed of light, and then the mass shoots up, and then you get too large mass and too small space, if you reach Schwarzschild greatest density, critical density, yeah, it might create a black hole. So, oops. Relativity equations for time, length, and momentum. Hold true for. Yeah, both of the above. This is called the correspondence principle. So not only does theory of relativity have to explain all the wacky physics that allows like GPS satellites to work in a little bit, right? Like relativistic speeds, but also they better be consistent with what Newtonian physics already pretty accurately predicts, right? So all last semester stuff, which is also true, right? If your speed is pretty close to zero, then those dilations don't have very much effect at all. Yeah. If you travel close to the speed of light, you would notice what yeah, you would notice nothing weird inside your own rocket ship. Yeah. Only an outsider would see something weird, or if you're inside the ship looking out, the rest of the universe might look weird. Inside it's fine. And if Einstein's equations for special relativity are valid, they must what? Yeah, all the above, all those statements are true. Again, that's correspondence principle, right? Correspondence principle. And last one for the win. 10-meter long sphere thrown at a relativistic speed, like maybe half the speed of light, through a 10-meter long pipe. But those 10-meter lengths had been measured when each of the objects were at rest. So at rest 10 meters, 2 meters. But now speed up to relativistic speed. When the sphere passes through the pipe, remember that train paradox yesterday? That would be a really helpful example for this one, really helpful model. Train paradox. Now, there was no 45-second Kahoot option. 30 seconds or a minute. Oh, yeah, you guys got that. Right, nice. Yeah, so any of the above, depending on your frame of reference. So if you assume that the pipe is at rest and the sphere is moving, which is really close to how the premise was framed, then the answer would have been the sphere shrinks so the pipe covers it. But if you're along for the ride with the sphere, then you would perceive the red one to be true. And if you're maybe moving at some medium speed, maybe like a quarter speed or something, right? Then you could actually calculate how fast you have to go on for the blue one to be true. Yeah. To the podium. Joshua, pick up the bronze. Olivia, hit the silver. And the gold. And Kaylee. Bridget and Israel. Runners up. Nice job, guys. Just my, okay, just my mouse. Here we go. All right, let's flip back over and knock out the rest of these problems. Yeah, so we're done. All right, so next one we got lined up is number 6. Did I read this one to you guys yesterday? Number 6? Okay, not yet. Okay, so But I think we did do number 4, right? We did number 4? Yeah, okay. So number 4 was you have some amount of mass. Let's say you convert it completely into energy. How much energy is that? So E equals mc squared. Now, really, this would be a mass difference. Let's say you start with some nuclear material and run some reaction. Say you were missing some amount of mass. Or this could be antimatter, and you could do a pure matter antimatter reaction. Right, so number 6 just couches the story a little bit different. It's still going to be E equals mc squared, but I want to put a little bit more context to this. So it goes like this. You are a resident of a space station moving between stars in a galaxy. In order to sustain a decent standard of living, you want to consume an average of 40 kilowatt hours of energy every day. Now, where do I get that number from? What does that mean? Because actually all of us right now, being citizens of a developed country, are using energy at about this rate every day. And you might say, okay, well, what do you mean like use this energy? Is that just like electricity bill, like running my laptop and my cell phone and the projection and the lights and the air conditioning? That's part of it. The gasoline you put in your gas tank in the car to make it go, that's part of it too. But also everything you buy, there was some assembly line process involved in that. All the groceries you buy, there was a whole agricultural process behind that. So you add in all those factors, all the clothes that you're wearing, right? There was energy that goes in, right? So yeah, people in first world countries, right, this much energy per day. And so let's just copy paste that, take that up into space. The fuel storage contains only the given amount of fuel, like this much mass per resident. So how long is this fuel going to last before it runs out? Okay. So, and let's say this is antimatter, just to make it the equation run. Okay? So we got 0.01 kilograms of antimatter, or you guys have whatever you have on your page, which I'll pick up. I'm gonna pick up this page soon. Tomorrow we'll do a speed of light puzzle. So I'm thinking by the end of the day tomorrow, and then as long as you guys have done all the problems, just follow along with me, then we'll be good. So now 0.01 kilograms. Guys, how many grams is that? Can you guys convert? It's a factor of 1,000. So if you take 0.01 kilograms and multiply by 1,000, that brings you up to 10 grams, which is, this guy right here. This is your guys' smallest lab mass. I want to say an American cent coin, like a penny, is about 2.5 grams. So maybe like 4 pennies or this little tiny lab. Okay, so let's say you have this much antimatter. So you've got it in some like magnetized vacuum container where it's not going to react with anything. You just a little bit, run some nuclear reactor. And so that's a tiny amount of mass. And what I want to put is through some nuclear reaction and then use energy at the rate that you've been using it your lives living in the States. And how long is that going to last? Right, so 2-part problem to this. First part is going to be E equals mc squared just to get the amount of energy. So it's that E equals mc squared. The second part is we're going to convert this to how much time, but first part first. Now I have 0.01 kilograms, and I do have to put everything in kilograms because that's the base SI unit for mass. Although you guys did tell me that's also 10 grams. And multiply it by 3 times 10 to the 8 meters per second feet squared. Okay. Now, only the speed of light itself is squared, not the mass also. So how much energy we're talking about in joules? 0.01 times open parenthesis 3 times 10 to the 8 closed square. Looking at the number is so big it doesn't even fit on my calculator screen. That calculator tells me scientific notation. 9 times 10 to the 14 joules. 9 times 10 to the 14 joules of energy. Woo! Okay, that's a big number, just like yesterday, number 4 was a big number. Great. What does that really mean? Well, here's where the story kicks in. So this is why I was telling you, okay, we're on some spaceship, we're consuming energy at a certain rate. How long is it going to last? And the answers are all some number of years. Ooh, some number of years. Huh? That what? Little 10 gram mass going to last? Seems pretty crazy. I give you guys a dimensional analysis table, which I want to walk you guys through because Ideally, this dimensional analysis table is something that you should be able to come up with on your own. I mean, someday you guys are going to graduate high school, go out in the real world, and there's probably going to be some applications of this tool right here that would be really handy to know in the future. So walk you guys through this. Also, the table I gave you is incomplete. There's a piece missing, so oops. But the first part says joules per resident. So I got 9 times 10 to the 14 joules per resident on board the spaceship. And okay, so we want to go through some process where you convert this to some amount of time, and maybe like years, because all the answer choices are years. But the rate that you're using energy, I told you in this weird unit of kilowatt hours per day. So let's take a look at that unit. So 40 kilowatt hours per day. This is something like that, right? Now, what I want you guys to see is, because someday you guys are going to pay a utility bill, they're going to say you use this much electricity, so you owe us this much money for the month for your electricity bill. Okay? And that number is going to be reported in kilowatt hours. Okay? It might be like 1,000 kilowatt hours, right? So kilowatt hour. I want you guys to see that this is an energy unit. It's really weird energy unit. I don't know exactly how or why this became standardized, but it did. So we've got what we've got. You guys know that watts, isn't watts like joules per second? Is that true? Watts is joules per second. So that's energy per time. If you take energy per time and you multiply by a time unit, like for example, hours, watt hours, wouldn't that bring you back to an energy unit? Okay. Now it's not exactly joules because it's joules divided by seconds times hours. So we're mixing and matching different time units. Okay. But that would be an energy unit, wouldn't it? Now, you slap on the prefix kilo, that's just 1,000 of those. Okay, so 40 energy units, and then per day, per person. Okay, guess that? Right. And then per day, per person, you can, that's a fraction within a fraction. You can do like this, day, person. Right? Because fraction within a fraction. Right. And that's what's gonna pop in right here, except it's gonna go in upside down because we want to cancel out the energy so we get time units. So this will solve both problems. It'll cancel out the energy and also bring time to the numerator. So I'm going to go 40 kilowatt hours per day per person. And well, we've got resident, so I'll do resident. Okay. Right, so see how energy and energy is eventually going to cancel out? Not exactly yet because the units don't match, but set up to. And residence cancels. And I have a time unit on top, which is good because I want my final answer to be some kind of time unit. But I want it to be years, not days. And also I have to reconcile joules and kilowatt hours. So we need that. Well, how about this? Let's take care of the kilowatts versus the joules. So I know that there are 1,000 joules per 1,000 joules per second is equivalent to 1 kilowatt. Right? So 1 kilowatt second and 1,000 joules are the same thing. Okay, so this is a ratio of 1. It goes back to the theory of how dimensional analysis works. So joules and joules, kilowatts and kilowatts. But I still have to reconcile the time units because it's got days, seconds, hours. So well, I know there are 60 seconds in a minute, 60 minutes in an hour. So that's 2 small steps. I'll just combine those and say there are 3,600 seconds per hour. So hours, seconds, and now I've got how many days this fuel is going to last. Now that's as much table as I printed on the paper, but we're going to go one more step and say that there are 365 Earth days and 1 Earth year. So I know we're up in space, but let's say we're still using the Earth calendar. And so we've got something. Okay, so now days goes goodbye. And I'm going to get some number of years comes out of this process. You guys see that? Open up calculator, multiply across the top. 9 times 10 to the 14 times 1 times 1 times 1 times 1, all divided by, open parenthesis. I got 40 by 1,000 by 3,600 by 365. And that is, oh boy, 17,000 years. Wow. Yeah. Now make sure that everything in the denominator is grouped together in parentheses. See how I did divide by and then open a parenthesis? Okay. So it's all grouped together in the denominator. Okay. And you should get something, I mean, everybody has different paper with different numbers on it, but you should get something like this order of magnitude, like about 10,000 some years. Okay. So, woo. So if you had this much antimatter right here, and use it at a rate of, convert that into energy, nuclear reaction, and use that at a rate that you've been using energy your whole life, yeah, it would last you 17,000 years. Wow, that is the power of nuclear energy right there. Working out your gas. Right. Number 7. As you speed up and approach the speed of light, your length as seen by a non-accelerating observer, I should say inertial frame of reference, appears to do what? You're going to get, sorry, I'm looking for some graphs. Oh, here they are. Okay. You guys remember these graphs from yesterday? Okay. So as you speed up and approach the speed of light, your length appears to shrink down, so you get shorter. But the train going through the tunnel look like it got shorter. Okay. Number 8, as you speed up and approach the speed of light, your mass appears to do what? That's this graph here, speed up. So scientists over at CERN see the mass of these particles going up, tending towards infinity. Okay. That's why they were afraid of creating a black hole back in the day. But they tried it out, no black hole, so we're still alive, everything's all right. And a nuclear reaction, which is following, is taking place. Nuclear reaction, that's E equals mc squared. E equals mc squared is the equation of nuclear reactions. So I would say this one right here, mass is converted into energy. That's mass energy equivalence. If you know how much mass converted, that's what we just did with all this dimensional analysis table. Okay? That's what kickstarted it. There was some amount of mass, convert to energy, and did the extra step. How long does that last for? In the mass dilation equation, this one right here, what happens to mass as v approaches the speed of light? Oh, you know what I should have been doing for these last few questions anyway was referring to the dilation equations, because I don't want you to just like memorize the story answer, but to be able to navigate the equation and make sense of it too. Okay, so we discovered this anyway, right? As you approach the speed of light, doesn't your mass tend towards infinity? Okay. But let's say you didn't have this graph, or you forgot this, or it's a few years from now and you're taking another physics class. How can you figure that out again from scratch? Well, if v approaches c, this ratio c squared over c squared approaches 1. 1 minus 1 is 0. Square root of 0 is 0. Anything divided by 0 is infinity. Okay. Number 11, time dilation equation. Solve for t when v equals about 0 meters per second. So say 2 observers are not moving relative to each other, or not very fast compared to each other. If you plug in 0 for v, this becomes 0. 1 minus 0 is 1. Square root of 1 is 1. Anything divided by 1 is just itself. So shouldn't it look a lot like this right here? Which is this intercept on this graph, right? Which is also the correspondence principle, right? Like you and me, not really moving relative to each other. And we both agree that time passes at the rate that it does. Okay. And yeah, number 12 we did yesterday. So you guys should have that whole side finished. Okay. And we'll save the other side for tomorrow. Oh, yes? 10 and 11. Okay, so number 10, as you approach the speed of light, what happens to mass? It increases how far? All the way up to infinity, right? And number 11, if your speed is close to 0, what's t equal to? That point right there. Oh, yeah.
Is number 7.
Number 7, as you speed up and approach the speed of light, your length is seen by a non-observer. So you go faster, faster, faster. Your length goes in 10 towards 0. Yeah, it gets closer to 0, which would be decreasing, wouldn't it? Okay. Guys got this? So I said we'll save the other side of this page for tomorrow, and got a few minutes left of class, so at least I'll start the last demo video for you guys.